Hello and welcome to the Ridley Engineering Power Supply Design Center in Camarillo, California. Today I'm going to be talking about loop injection transformer measurements. We've been working with and designing and specifying the frequency response analyzer from AP Instruments, also here in California, for over 20 years now. And we have a tremendous amount of experience with designing accessories for this instrument. And the most important one is the isolation transformer for loop injections. And here you can see our latest offering is our universal injector, which goes from 0.1 Hertz to 30 megahertz. This is actually the third isolation transformer in our line over the last 20 years. We started out with 10 Hertz to 5 megahertz, extended that to 1 Hertz to 30 megahertz, and then 0.1 Hertz to 30 megahertz. We have a lot of experience in doing this with our third generation, and every time we improve it, the transformer's gotten a little bit bigger to extend the low frequency range down to measure power factor correction circuits and other low frequency circuits very carefully with a decent signal. We've been doing this so long, we've made our mistakes along the way, but we've come up with a very good product now that we kind of feel like we know what we're doing here. So we're always surprised when we see papers and other products trying to appear on the market that claim to have a much better design. There are two other transformers here. One we're going to call it Unit P is supposed to go from 1 Hertz to 5 megahertz. And another transformer we have here, we'll call this one Unit O. It's also supposed to go down to 1 Hertz and up to 10 megahertz. And we notice right away both of these transformers are really quite light compared to our injection transformer, which as a magnetics designer of many decades, always raises a flag with me. So let's take a look at that. Let's try and weigh these transformers and see where they come in relative to each other, and then we'll take a look at the electrical performance and see how well they work. So here's our scales. Let's put the first one on here, which is the Ridley transformer. So there's the 0, and you can see right here we're measuring in at 695 grams on this transformer. And it's pretty hefty in your hand. Second one is Unit O. And this just measures a scant 229 grams, less than 1/3 of the other transformer. And the final one, Unit P, measures 225 grams. So you can see both of these units here are kind of lightweight, which kind of concerns me about how well they might perform down at low frequencies. So we're going to put this into our circuit and test this out now and see what the signals really look like from these different offerings. Right, what we're going to do now is test these three isolators electrically. So this is the setup that we have here. First we start with the AP300, that's our instrument on the right here. We're going to take the source output from that, using it as an RF power amplifier, and then we're going to drive a splitter with 350 ohm resistors in it, and those splitters will drive each of our isolators. So we make sure this way that they're all getting the same drive signal. So here's the Ridley isolator, is Unit O, 1 Hertz to 10 megahertz, Unit P, 1 Hertz out to 5 megahertz. And what we're going to do is look at the actual output of each of these devices to see how they perform with this drive. So let's switch over to our waveforms now. So here is the control screen for the AP300, and we control the output signal by pulling up and down this green line here. So we're initially going to set that at about 1 volt, and our start frequency is 10 Hertz, our stop frequency is 10.1 Hertz. So that's 1 decade above where each of these transformers is supposed to be working. Now as I slide this green line up and down, you can look at the yellow curve here. This is the output of the AP300. So you can see it driving at different levels at 10 Hertz here. This is just 10 milliseconds per division. So put that down to 1 volt again. Right there. And you can see on the output of the Ridley isolator, that's the purple curve here, we're getting a very clean, undistorted sine wave, and it's about a 2 to 1 or 3 to 1 attenuation at this frequency. However, on unit P here, which is supposed to go all the way down to 1 Hertz, we can see that the transformer is saturating quite badly. And not only is it not giving much signal on the output, but it collapses almost immediately after the sine wave starts. So if you try injecting this distorted sine wave into your power supply, you're going to get some very bizarre results coming into your system. Unit O also has distortion. These are different from each other, obviously a different transformer being used here. But again, this one is saturating very badly and is really not usable with a 1 volt signal down at 1 Hertz. I'm sorry, a 1 volt signal down at 10 Hertz, which is well within the specification where this is supposed to be working. But the Ridley isolator is working just fine. Let's turn the signal up a little bit more. So on the output of the AP300 we have an RF power amplifier built in. Very convenient for driving your power circuits hard. So we're going to move this all the way up now to 7 volts RMS. We'll turn down the signal size there on our scope. Bring that down. You can see that. It's just about 20 volts peak to peak. And you can see at the output of the Ridley injector we're seeing, plus or minus almost 3 volts coming out, completely undistorted. The other 2 units, they don't have a chance of working properly. If you inject that into your power supply, you're going to hear all kinds of noise, buzzing, transient response, and the control loop is going to go crazy trying to respond to this. So you're just not getting a decent injection level into your power supply at this point. So these units, which are definitely lightweight when they hit the scale, really are not doing a very good job down at these low frequencies. They're not usable. Let's take it down a little lower in frequency. Let's go down to 2 Hertz. I want to do 1 just because it takes much longer for the scope to sample. Oops. DC coupling. And make this 2 Hertz to 2.1 Hertz. I'm still going to put in a decent sized signal here. And we'll change our time base. Okay, what we're doing now is we've reduced our sweep frequency down to 2 Hertz, going from 2 Hertz to 2.01 Hertz. And we're starting out on our scale here with our drive from our amplifier at just about half a volt. You can see the signal coming out of the AP300, nice undistorted sine wave. Coming out of the injection isolator from Ridley Engineering, you can see again a beautiful undistorted sine wave ready to drive your power circuit hard. Coming out of unit P, that we can see that we've got terrible signal now, certainly not usable, less than 100 millivolts, saturating badly, all kinds of harmonics involved in this signal. Same story with unit O, that's just not going to work for you. Less than 100 millivolts coming out of that isolator as well, and these just aren't usable for for any kind of power supply work. Let's turn the signal up a bit more just to see how far we can take the Ridley. So here, going all the way up now to 7 volts RMS. Change the scale on the reading. And then you can see a nice healthy power amplifier signal, almost 20 volts peak to peak. And then when we look at the signal coming out of the Ridley unit, we got lots of power here. So we're getting almost 5 volts peak to peak, ready to drive our power circuits at these low frequencies. The other 2 units, completely unusable. You can't inject a narrow pulse like this. They're just going to hit transients and respond badly. That's if you don't blow up your power supply. So again, you can see, these units here, they don't weigh in well. They don't have enough magnetic material, and they're not going to inject a decent signal into your power supply to make the measurements that you need. So you just can't use them for anything like a power factor correction circuit or any low frequency measurements. And this effect extends beyond 10 Hertz. It goes all the way up into the tens of Hertz before they actually start passing a good signal. So there you go. That's our comparison for you. You're all welcome to go do these experiments yourself. And now, just to summarize that, if you want an injection isolator that truly works, we've been doing it a long time, so don't look to try and find it somewhere else. Don't try to find a lightweight unit, and we don't really recommend you try and build these yourselves. Can you do it? Of course you can. Just spend about a week and for that you could have taken the same amount of money in your time and bought one from us that works a lot better. So we have 20 years of experience in building these. It's not really something that you need to reinvent. To learn more about this and power supply design, come to ridleyengineering.com and go to the Power Supply Design Center, where you'll find over 100 design papers, tips, measuring frequency response, magnetics design, and power supplies. If you want to get more first-hand experience, come along to one of our power supply design workshops here in Camarillo. Thanks for watching. Stay tuned for more videos.